of a plate that's 50 millimeter wide, 2 millimeter thick, and 500 millimeter long, fixed at one end. So the buckling length is 1 meter, 1000 millimeter. The critical buckling load from the Euler's formula is pi squared EI over the buckling length squared, which gives 65.8 Newton. The critical stress is 0.658 MPa, which is way smaller than the yield strength, or the first stress at yield. And because we know how this will buckle, I will consider this as a two-dimensional problem, and I will consider the unit width of the plate, and in this particular case the critical load for a unit width is 1.316 Newton. A buckling problem is dependent on the imperfections of the geometry. So I'm going to show you, I'm going to solve this problem twice. Once without any initial imperfections, and once with initial imperfections, to show you that the results are totally affected by a very small change in the initial geometry. So let's start by a perfect geometry from 0, 0 to x. The thickness of is 2 millimeter and the height is 500 millimeter. Done. And that's mesh. I maybe have 2 millimeters, so let's have 0.5 millimeter for an element size. And of course this is a structured mesh would be adequate for this. And let's use plane stress, reduced integration. Okay, and then mesh this part. Yes, let me just check the mesh. Looks good. Material, elastic, Young's modulus is 200,000. Poisson's ratio is 0.3. That's plastic. I'm gonna copy the stress strain curve. These are the data. Paste. These are the stresses. True stress versus plastic strain. Paste. Okay. Sections. Continue. Okay. Assign section 1. Assembly. Bring the part. Okay. Create a step. Now this step is a static Rix. Nonlinearity in the geometry. And since I don't know the maximum load, I should limit or make the model stop at a certain displacement. So first I need to identify a set. So I'm going to make a set geometry. So geometry set 1, and let's look at this node, and in my step let's stop when the maximum displacement reaches 250 millimeter, degree of freedom 2 of set 1. Okay. So let's apply the load and the boundary conditions. So let's apply the value of the critical stress at the top portion. So we're applying traction actually. So surface traction, because we want the forces to always be vertical even after the rotation of the surface. Select the surface, so this is the surface of the load. Now this traction is general, and you have to not follow the rotation because we want it always vertical, and the value of the force is per unit undeformed area. I need to define the direction. So the direction is, the first point is 0, 0, enter. The second point or direction vector is -1. And here is, I need to put the value, so the value of the stress, let's just put a unit value of stress vertically. Okay. Then we need to apply the boundary conditions. Let's fix the bottom part. This region done. Fix, and this is it. Create a job. I'm gonna call this job B. Continue. Alright, and submit. So after the analysis has been done, the first thing I will check is the status file, which is the file with the extension STA. So looking at this file, this is the load proportionality factor, which tells me how much load has been applied to the structure. If you remember from the previous lecture, we talked about the lambda parameter. This is the lambda parameter in a Rick's method, or in a line art method, as we talked about it last lecture. So this shows that the critical stress of 1 that we applied, actually the force applied at the end after 100 increments is about 1580. So clearly the structure has not buckled. But let's look at the results. So I'm going to open the ODB file, and the first thing I'm going to look at is the deformation. So looking at the deformed shape, it clearly has not buckled. So since the geometry was perfect, or perfectly rectangular, and the load was was perfectly symmetric, the structure shows no signs of buckling. And if we look at the stresses, I'm going to look at the von Mises stresses. Contour, it's 1.197 times 10 power 3, which is the maximum, the ultimate stress of the material. So basically this column or this plate has been compressed up to the ultimate stress without reaching any buckling. And of course, physically, this is not possible. So let's see how this will change when we change the initial geometry. So I'm gonna go back to my model and go back to my sketch and delete this sketch, or actually delete the geometry that's in this sketch, and redefine my geometry and just give it a little bit of perturbation. So start at 0, 0. The width of this plate is 2 and y 0, and then let's have it slightly to the side with a value of 0.1 millimeter. So let's give x 2.1 millimeter, y 500, x 0.1 millimeter, y 500, and go back to 0, 0. Done. I have to now right click on feature and regenerate my sketch, and now this has been moved 0.1 millimeter to the right. Now I just want to make sure that the loads are applied at the exact location. Probably not. I have to edit the region. Now this is applied on the top. Okay, and the boundary conditions as well. I have to edit the region and apply the boundary condition on the correct side. Okay, and also set 1, which I created to monitor the displacement. Set 1, reselect the geometry of the set, it's this one. Done. Now let's run it again. Submit. Oh, I forgot to mesh it. Okay, go back, mesh, nothing's changed. Okay, all I have to do is just mesh it. Yes, and submit. Okay. Now looking at the status file from this analysis, we see that the load proportionality factor is actually 0.377, 0.6, 0.7, and the maximum after 44 increments is 0.839, which means we have not reached the maximum critical stress of 1 MPa that we applied. And the analysis stopped after 44 increments, and it says the analysis has completed successfully, which indicates that the trigger, that probably the condition of the displacement of the 250 millimeter maximum displacement has been reached. So let's look at the results. Open the ODB file and let's look at the displaced shape. Indeed, the structure has buckled. So a 0.1 millimeter, a slight imperfection in the geometry has totally changed the final answer. Now let's look at, I would like to know what is the load that the structure has reached, what is the load displacement curve of the structure, and I also want to verify this with the reactions. So the first thing is I need to print the load proportionality factor. I can either get this from the status file, so this is the load proportionality factor, or I can print it from here. So this is an ODB history output, load proportionality factor for the whole model, plot, and you can see that the load was increasing and then it's horizontal, indicating buckling, and then it started increasing again. I'm going to report this, and I'm going to call it lpf.rpt. okay. Or I'm going to I probably have it open already. So lpf.rpt, okay. Already exists, okay to overwrite, yes. The next thing I will want to print is the displacement of the structure. XY, this is a field output. I would like to plot the displacement. Let's plot the vertical displacement of this node. Plot, and this is the vertical displacement. Report XY, this displacement, I'm gonna call it, and just make sure that I don't have any other files with the same name. I'm gonna call it displacement.rpt, DISP. okay. Overwrite, yes. Then other thing is also I want to verify the reactions. So it's a field output. I would like to print the vertical reaction, and of course the vertical reactions are from the bottom nodes. So edit selection, these are the nodes that had vertical supports. Plot, so these are the reactions, and I'm going to write a report, and I'm going to call it, so just pick the reactions, and I'm going to call it RF. Make sure I don't have any RF. Okay, yes. Now I'm going to analyze all this using Excel. So for this problem, I know that the Euler buckling load is about 1.316 Newton, and the stress at this instant is, or the Euler stress is 0.66 MPa. So I'm going to open the load proportionality factor report and make sure that the data is separated. So this is the arc length, load proportionality factor. Remember, the applied stress was 1 MPa. The area is 2 millimeter multiplied by 1 millimeter, so this is millimeters squared. So the force is equal to 1 multiplied by 2 Newton. So the actual load is equal to the load proportionality factor multiplied by the applied force. Hence, the actual load, this is the actual load, and let's see how this changes with the displacement. So I'm going to open the file displacement, again ensure the data is separated, and I just need the displacement data to put it here. So displacement, so when I put the displacement versus load, let me take this as positive. versus load. You can see that at around 1.25 or a little bit higher than 1.2, the structure totally changed its direction, totally changed its path. So going back, remembering that the critical load was 1.32, so it's because of the slight imperfection, the structure buckled at a slightly lower displacement, or a slightly lower load. And let's just take a look at the behavior at the buckling, at the onset of buckling. And let's maximum displacement, let's have it at 0.2, or let's say 1 millimeter. Let's have it at 0.1 millimeter. So you can see that the load was increasing, and at some point this load displacement curve became horizontal, which means of course that if I did not use the Riggs method, I would not be able to capture this behavior. I also would like to ensure that my numbers make sense, so I'm going to find the reactions and ensure that the reactions are equal to the actual load that I just calculated using the load proportionality factor. So I'm going to open the reaction file. Make sure that the data is separated, finish, and just sum the reactions. These are just the vertical reactions. I'm going to sum these numbers and copy this value, go to the report and paste values, and these are the reactions. Indeed, the reactions and the load are equal, which indicates that I know exactly what I'm doing. Now let's look at the stresses just to explain what is happening. So let's look at the results. Field output. Let's look at the von Mises stress. You can see that although the structure is unstable, the stresses are actually not the stresses were right now at about 800 or 760 MPa. The ultimate stress is actually 1200, so material wise it has not reached the ultimate stress yet. It's the problem is unstable, and any slight increase in the load will lead to collapse.